Hi, so I'm just going to review one of the questions that we didn't quite get finished in the lesson. You can see on the screen there I've captured the whiteboard from the lesson, and the issue came up around this large function here, x cubed, this one here, x cubed plus 5 over x to the 6 plus 2 over x minus 4e to the minus 4x dx. We're trying to find the indefinite integral of that. And we worked through most of it, and then we got to this point here where we stopped and asked, is that the correct answer? And then we ran out of time. So let's take a look at that one. Let's take a look at this piece here on its own. We've got 4e to the negative 4 of x, and we are going to find an indefinite integral for that, antiderive it. The important point to remember is that when you take functions like this, e to the power of something, then when you integrate them or when you differentiate them, they return the same part as core of the answer. So we have this bit as the core of the answer. The step that we haven't completed yet is when you differentiate, you're going to multiply this bit. So that would be 4 times minus 4, which was the negative 16 we thought we had here. But we are not differentiating. We're going in the other sense. We are integrating. We're finding the antiderivative. So what we have to do is divide by this number here. So we're going to end up dividing by negative 4. So our antiderivative, our indefinite integral of this number here is e to the minus 4x, and it's got a negative sign there from the negative 4 down there. And when we take this piece here and we put it back into our expression up here where there's a negative sign, we're going to get a positive sign to finish off. So our final expression then is going to be x to the 4 divided by 4 minus x to the minus 5 plus 2 times the log n of x plus e to the minus 4x. And then, just to make sure we've completed it, we put our constant of integration on the end. Now, to show that that actually is the correct one, what I've done on the other side here in Desmos is actually to plot the two functions, the original function up here and its definite integral, which we've got down here. So remember that if this is the definite integral here, going that way, then remember that the connection between these two means that this is actually the derivative. So if you take this function here and differentiate it, you get back to the original function up here. So that the antiderivative, what we call the indefinite integral, is balanced by going the other way to give our derivative. And if we actually plot those two on a chart in Desmos, okay, this is what you will see. So the yellow line, the orangey line in this case, is the integral of the blue. Here's our original function up here in blue. Up here in blue, that's that function there. Does a bit of a loop around. The integral that we found is this strange line going up and down here. Okay, and the green line I've added. The green line is the point where this blue line comes down to its minimum, 1.3243, and then it heads back up again. And all that is describing is the slope here on this function here. The slope is coming up, it's getting less and less uppy until it reaches a point here. So here, which is the derivative, remember that's the original function, it's up, gradually comes to a low point and then starts going up again, which is what you see happen here. It's up, but it's getting gradually less steep until it hits this point here, and then its steepness increases and goes on off the end of the chart. Okay, so that's just to illustrate that this antiderivative here, this integral here, really is connected to that function there. The original function we had is actually the derivative of the antiderivative that we have found and plotted here. And you can see here there's a point on the chart here where the steepness of the line changes. It changes from getting less and less to a point where it gets more and more. And that point we're going to learn is called an inflection point. It's not a turning point, it's not a maximum or a minimum, it's an inflection point. Okay, that's all I wanted to say about that particular function and what it looks like on the chart. Hope you take a chance to look at this and understand the error that was being made before the lesson came to an end. Take care.